Hello there. How are you guys doing? I can barely see a single soul here. There's maybe like 2 people in the room, right? All right. And unlike me, this is awfully bright here, but hopefully you can see me well that way. Okay, so welcome to Vancouver and to this year's edition of SIGGRAPH. I hope you're really excited about this week of event coming up. I'm guessing you're here tonight because you want to see the special screening of Jurassic Park, but before we get to that, there is the papers fast forward. So bear with me and prepare yourself for an intense, fast-paced, and hopefully IQ-raising overview of all the papers that will be presented next week. Year after year, the fast forward, in my mind, it epitomizes the intellectual wanderlust that our community is well known for, and it's basically the modern version of flipping through the proceedings, except that it's more informative. This year, I've had the duty and pleasure to supervise the selection of the technical papers program, and what you're about to see in accelerated form represents countless hours of dedication and hard work. We started with 464 slides. I realize that I don't have my switcher, but that's okay. Each of which got reviewed by at least 5 experts with both great care and an obsessive attention to fairness. After more than 2 months of reviewing and over 10,000 messages exchanged between reviewers, the papers committee of 60 experts met in Chicago to decide which of the submissions would be presented this year at SIGGRAPH. 128 papers made the cut. And tonight, finally, you'll get to get a glimpse at them all. Along with an additional 39 talk papers that were published over the last year, all these papers really represent the current state of our scientific field. I don't want to take too much time on stage, but I have to thank a large number of people that helped with this program. Without them, there would be basically no program. First, I'm very indebted to the 60 committee members who took the time to deal with all the submissions. You can see them right here. As you can see, they're all beautiful human beings, but to be honest, that's not why I entrusted them. That was really their brains that I was after. And they delivered quite nicely, so I would like you to give them a huge round of applause. And I'm not going to read the names of all of them. I apologize, that's just 60 people. Okay, for the next slides, I would like also to thank people that I worked very closely with. For starters, there were the sorters that helped me sort through the submission and distribute the submissions to the committee members. So you see the names. Let me just mention their first names: Kavita, Aaron, Doug, Paul, Simon, Peter Pike, Olga, and Ying. There was also the advisory board and the 3 future chairs of SIGGRAPH or SIGGRAPH Asia technical papers programs. All these people really helped me not only by being there, so I felt like it was moral support, but also to give me advice when I really needed some, so that was perfect. And finally, I would really like to thank some of the people that really did the heavy work, the heavy lifting in this program. Really, without them, there would be, nothing would be even remotely possible. So I really have to thank them all. So let me go through some of the names: Leona and Elijah, Mark for the system links, Steven Spencer for assembling the proceedings. This is a huge task, and I'm so glad that somebody did it and not me. Adam and Tom assembled the trailer. I don't know if you looked at it, but it's fantastic. Roy, of course, for entrusting me into this task, the fool. He didn't know who he was picking, but anyway, I loved working with Roy. And finally, Munu, who assembled this whole show. So whatever you're seeing tonight, Munu did it with her team. I want to give a special mention to both Leona and Mark, because they really became like a second family to me. Because we had to meet several times a day sometimes. So it was really fantastic to work with them. And of course, Munu, because she makes us all look good, so that's nice. Finally, and there's no slide for this, but I would like to acknowledge all the authors of submissions, even those who didn't make it to this year's program, because you guys are really the most crucial element of the technical papers program. Because without your passion and creativity, well, there would be nothing to review, but therefore nothing to learn from. And even if your submission did not pan out this year, please try again, because our community really needs your best work to thrive. That's it for me. I wish you a great show, but I now leave the floor to Angus, who will say a few words about his Art Papers program and how to follow along the fast forward with your cell phone. Thanks.
Thank you, Matthew. I'm Angus Forbes from UC Santa Cruz's Computational Media Department, and I'm the 2018 Art Papers Chair. This year, we're including some of the art papers in tonight's Fast Forward. Art papers discuss innovative new media arts projects or investigate the cultural opportunities and impacts of media technology. We had well over 100 submissions from artists and researchers around the world. The accepted papers will be presented during 2 art paper sessions on Tuesday and Wednesday, and are published in a special issue of the Leonardo Journal of Art, Sciences, and Technology. I want to give a huge shout out to our esteemed Art Papers jury on the next slide, who worked so hard to manage the reviewing process, as well as to all of the folks at Leonardo, next slide, and Smith Buckland, and to the many members of the SIGGRAPH community who contribute to the success of the Art Papers track. Tonight, we're going to see a total of 172 fast forwards presented in the order of their schedule during the week. Next slide. We encourage you to follow along with the show using the SIGGRAPH 2018 app. On the app, navigate to Papers Fast Forward. All of the papers are conveniently listed in the order that they are presented tonight. When you've seen a presentation about a paper that you are interested in, tap on the circle next to its title, and it will be placed in your favorites list on the app. Then from within the favorites list, you can quickly navigate to the presentation tab and then add the appropriate session to your personal schedule. Next slide. We'd like to conclude this introduction by recognizing Adobe's generosity in sponsoring these fast forwards, so let's give them a round of applause. Thank you, Adobe. And without further ado, please sit back and enjoy the presentations. Thank you.
Distortion optimization is popular in graphics, but usually time-consuming. Second-order methods has good convergence rate, but suffers from expensive system solved during each iteration. First-order method is efficient pre-iteration, but converges poorly. We propose a novel optimization technique, Bacon, that avoids second-order method sufferings and also has good convergence rate by combining a Crossing-Newton method with a search direction current technique. To find out more details, please come to our talk.
Master, how can I jump to the bottom fast?
What do you think?
Follow the negative gradient direction.
Too slow.
Well, use the Hessian information of the convex proxy function to get a better descent direction.
Better, but it can be faster.
Give me some tips.
Choose the point between your position and the bottom as your temporary target, and then repeat that.
Can you explain it in more detail?
So this is our method, fast and robust. Thank you.
Iterative solvers has been widely used in geometry optimization and physics simulation. However, its slow convergence limits the application extremely. We proposed a simple and neat method to accelerate the convergence of it. Moreover, we show the effectiveness with wide of interesting applications. To learn more, please come to our talk tomorrow. Thank you.
Real-time nonlinear least squares optimization is pretty important in the SIGGRAPH community, but the traditional development process for these solvers results in lots of gnarly GPU code. Beyond that, it requires months of grad student mental and physical exhaustion to produce. But the results are stunning, with solvers orders of magnitude faster than high-level ones. But it could be easy. We introduce opt, which takes short, high-level specifications and generates even faster GPU solvers automatically, so you can have your time back for other things.
Given a complex deformable body and high-level objectives, we generate active animations. The deformable body moves around by interacting with the environment, and our system requires minimal user specification. Our system can generate various locomotion gaits, such as swimming, jumping, rolling, and walking. Please come to our session for more details.
Thank you.
The generalized winding number is great for robust inside-outside segmentation. However, it is slow for disconnected triangle soups and has no definition for oriented point clouds. Our method asymptotically accelerates the winding number, making it feasible for triangle soups. Furthermore, we define the winding number for oriented points, enabling novel applications such as direct 3D printing of point clouds. And our method is up to 1,000 times faster on real-world examples. I hope to see you at my talk.
The medial axis has many applications in computer graphics. However, computing the medial axis of a three-dimensional shape is still a challenging task. We present a simple method that works as follows. We first voxelize a shape, and then we take a subset of the Vonoy diagram of the boundary voxel vertices. Our method is efficient, numerically stable, and is equipped with theoretical guarantees. Hope to see you in our session. Thank you.
We propose an algorithm for topology-correct surface reconstruction. From an exponentially large collection of possible reconstructions, we select the globally optimal topology-correct solution. Our branch and bound framework leads to a better result in comparison with state-of-the-art dynamical programming methods. To hear more, come to our lecture.
We propose a novel approach to the classical implicitization problem. For a given parametric surface, we compute three moving planes whose resultant gives the implicit equation. Our method is more efficient than typical implicitization techniques such as Mil basis and Gravana basis. When implicitizing the utility port, our approach is comparable in efficiency with the latest SIGGRAPH work, but first achieves theoretical completeness.
So, thank you. Welcome to my talk.
Revealing the magic behind photo retouching is challenging. Black box deep learning approaches help little because people do not retouch photos with convolutions. Instead, they use stepwise high-level operations. Our human understandable photo retouching model can be learned using reinforcement learning and GANs. It not only generates good photos, but also steps to get those photos, so that we can program artistic styles. In addition, our system has infinite resolution.
Thank you.
On screen is the famous Anderson illusion. This psycho-visual phenomenon motivates our new HDR tone mapping strategy that preserves local order statistics. Our main contribution is a linear programming optimization framework to maximize contrast, Weber's metric of contrast, while prohibiting contrast reversal. This greatly boosts the image quality without artifacts. Come to my talk, please.
There are many printed half-tone photos in different styles. Here, we present a descreening method. Given a half-tone image, we magically restore it. We also present a rescreening method. Given a natural image, we fantastically half-tone it. Okay, we have half-tone, descreened, edited, and rescreened. And now we can secretly change the history. Come to see us. Thank you.
Aiming at non-stationary textures, we propose to synthesize by learning the expansion from smaller blocks to larger ones containing them, so that we are able to expand this input while faithfully capture all the visual characteristics of the exemplar. The cool thing is that we can use the trained model repeatedly, so that we can generate huge textures like these ones. And we can also transfer textures to a whole different structure. Yeah. Please come to our talk tomorrow morning. Thanks.
We've had 30 years of groundbreaking achievements in the realm of physically simulated cloth, but the common trend has always been to avoid sharp collision features. Simulating the sliding motion of cloth over sharp geometric features can cause locking and failure. We introduce a new Eulerian on-Lagrangian simulation that augments traditional solvers in order to capture the sliding motion over sharp features correctly and safely. Please come to our talk.
Our wet cloth is open source. Please try it. Thank you.
Existing methods for cloth simulation handle contact and friction approximately, seeking primarily to avoid visual artifacts. In our work, thanks to an adaptive refinement method and an efficient solver, we are able to significantly improve the accuracy and realism of cloth simulation. Want to know more about our work? Come to our talk on Monday afternoon.
From the dawn of time, mankind has looked at the stars and linked the stars together. Many still wonders what the meaning of all this is. Clearly, there's people who are looking to integrate spherical harmonics on polygonal boundaries. And we introduce an efficient method for that problem and showcase many application scenarios. So please come tomorrow to our talk.
We present a method that extends pre-computed radiance transfer and allows for near-field area lighting by effectively computing higher-order spherical harmonics. We can translate lights, rotate them out of plane, or modify light shape with our additional pre-computations. The method runs at over 300 frames per second for the model shown on desktop, and ports to a mobile device that runs at 60 frames per second. To learn more, please attend our talk on Monday. Thank you.
Rendering realistic depth of field requires drawing large circles of confusion. However, filling all the pixels of such a disk takes a lot of time. In our paper, we suggest to only draw the circumference and to use integration to fill in the missing pixels. For more complex effects, such as this motion blurred circle of confusion, we optimize for a sparse differential representation to draw. Our method enables high-quality distribution effects at interactive rates, including physical and stylized point spread functions. Thank you.
When ray tracing animated content in real time, we need to rapidly generate acceleration trees. To do this, we propose a fast, cheap hardware builder which could be integrated onto a GPU. One main feature of this builder is the hierarchy emitter, which receives a stream of Morgan sorted triangles and outputs a BVH tree on the fly. For more details, please come to our talk tomorrow. Thank you.
Hi, I'm a biomechanical skeleton.
Ouch.
With over 800 muscles, I'm now a human musculoskeletal system. Wow, I definitely need some sensor motor control. Look, I'm training the 10 deep networks in my neuromuscular motor controllers. I've also trained the 10 deep neural networks in my sensory motor controllers. Now, I can gaze and track moving objects with my foveated eyes. Hey, look at me. I can perform sensory motor tasks like these. Yay! Another big win for deep learning.
Please come to our talk tomorrow.
Everyone has different muscle conditions and physical capabilities. We designed volumetric muscle model, which can reproduce various body conditions such as growth, paralysis, and the changes of muscle dynamics. Our system is not just for the simulation, but controllable system. We can make the model do juggling, which requires robust handling of the balls. Please come to our talks, more details.
Virtual clothing try-on has been a long-standing goal, but the body models have been unrealistic. We know how to simulate the physics, but the material properties have been picked almost arbitrarily. The human body is very complex, so we developed a new probe so that we can accurately measure how the human body behaves when it's touched. We've developed a new data-driven human body model. Please come to our talk to find out how. Thank you.
We need a tetrahedral mesh to represent the volume of a solid shape. But often the shape is represented by a messy triangle soup. Existing tetrahedral meshing algorithms fail or produce low-quality output. Our new mesher, TED-Wild, is robust and verified on 10,000 real-world models. TED-Wild makes no assumption about the input and always produces high-quality outputs. See you on Tuesday morning.
Hey guys, need to measure domain, but being straight is so limiting. We extend the Delaunay triangulation energy to higher order elements, and now curved is the new straight. Given a domain in blue, we can generate a curved 3D mesh, while each element is still as isotropic as possible. This method is very robust, and it can also handle sharp features. Come and see you talk.
Every remaining manifold can be isometrically embedded into some Euclidean space by large embedding. We present a novel method to compute a high-dimensional Euclidean embedding for arbitrary Riemannian surfaces and volumes. Based on the embedding, we can introduce new strategies for anisotropic meshings on surfaces and volumes, as well as some practical tensor fields. Please come to our talk on Tuesday. Thank you.
Do you want a simple method for realistically crushing a Coke can? Or maybe you want to see a sculpture of a hyperbolic disk. At least you certainly are desperately waiting for the bunny being turned inside out isometrically. Come to our talk, Shape from Metric, on Tuesday morning.
Cell phones take great pictures, but their small apertures make them incapable of blurring a distracting background behind a subject. Using just a single camera mobile phone, we present a system for simulating shallow depth of field. We achieve this by using a person segmentation neural network and depth from dense dual autofocus pixels. Our system is easy to use and has already been shipped to millions of users as portrait mode on the Google Pixel 2.
Dual lens cameras can take stereo photos, but the two views are very close together. Our method takes stereo pairs like these and magnifies the baseline to produce a continuous set of views suitable for VR. We convert a stereo pair into a new representation called a multi-plane image, which is a stack of painted transparencies arranged at different depths. When we view them from the front, the scene magically comes to life in 3D. How do we do this? With a deep network that watches thousands of YouTube clips. See you Tuesday morning.
I would like you to participate in the following short experiment. Please have a look at the scene. Now close your eyes, please. And now open your eyes again. Can you tell if the viewpoint in the scene rotated to the left or to the right? Those of you who think it rotated to the right, please raise your hand now. Well, you're lucky, that's right. We conducted several experiments to find out how much translation and rotation is possible in virtual reality during eye blinks. So if you're interested, please come to my talk.
The world can change a lot when we are not looking, which happens not only when we blink, but also when we quickly change our gaze position. We leverage this phenomenon of saccadic suppression for redirected walking in VR. Whenever the user makes a saccade, we slightly reorient the virtual camera. By doing so dynamically, we show how users can explore a much larger virtual space within only a small physical room without causing any extra distortion or discomfort. Thanks.
Have you ever had a teleconference in VR? Well, it should look like this. So half of the face is occluded, and you don't have an impression that I'm talking to you. Face VR is able to resolve this issue. We demonstrate stereoscopic real-time reenactment for HMD removal that is not only able to control the expressions, but also the gaze of the target actor. See you on Tuesday.
Do you like virtual reality? Do you like realistic face rendering? Do you like floating heads saying weird phrases?
When she awoke, she was the ship.
Then come on down to deep appearance models for face rendering. We create data-driven avatars using a multi-camera capture system. The main idea is to jointly model geometry and view-dependent texture maps with the variational autoencoder. We also develop a system to drive these avatars from cameras mounted on a virtual reality headset.
Our neural-based bodies can find sparse correspondence between images from different categories. We extract features from a deep classification network in order to find these semantic similarities. Yes, with these points, we can make a whole bunch of cool graphics applications. Want to hear more? Please come to our talk. Thank you.
Previously, we proposed a data-driven method that can arrange small indoor scenes, but not larger ones containing multiple furniture groups. We propose a new deep learning-based method that learns the possible locations of objects, as well as whether a particular object insertion is good or not. Starting from an empty scene, we apply 3 distinct neural networks to insert objects one at a time until completion. By doing so, we are able to create a variety of room-scale scenes with plausible layouts. Come to our talk on Tuesday morning to learn more.
Thank you.
There's been a great interest in applying deep learning to raw 3D data, such as point clouds.
However, designing networks that operate directly on point clouds is challenging.
We generalize convolutional neural networks to point clouds by extension and restriction mechanisms, allowing us to apply the standard 3D convolution.
To hear more, please join us on Tuesday morning.
Hi. Given an input airplane that just landed at Vancouver, we pick a point on it and hire a frog to take pictures around that point. We also ask the frog to pass these pictures to a special ConvNet we designed to produce a local shape descriptor for that point. Our descriptors have several applications, such as finding point-based correspondences between 3D shapes, matching shapes to partial scans, and also predict various useful affordance regions. Thank you.
We automatically create semantically coherent soft layers from an image in a process we call semantic soft segmentation. We use high-level features from a network together with the image to get these segments. The results follow the natural soft boundaries between objects. Semantic soft segments can be used for compositing with very little effort. And they can also be used for targeted image editing. Thank you.
Last year, our fast-forward video showcased iridescence in Unity. Sadly, no clear-code shaders were available when I started to work on the video, so I decided to work on it. However, I went further than clear-code and built an energy-preserved layered BSDF model that can take any number of textured layers and that work in real time. If you want to know how I made last year's video, come to the session.
Many materials like coated metals, skin, or plants are made out of multiple layers. We present a new method to render these accurately, including the complex effect of light interreflections. Compared to previous work, our method can also handle anisotropic materials, and we introduce a fascinating new inverse operation that lets us see inside a material. Please come to our talk to learn more.
The world is full of interesting color effects that can only be fully understood with wave optics. Our method can render arbitrary surfaces with wave optics, such as metallic cutlery, sandblasting aluminum common on laptops. This direct illumination shows the color effects more clearly, compared to the previous geometric optics solution. And here's a brushed aluminum example. See wavy optics on Tuesday.
In this project, we're looking to populate this scene with materials. This would require hours of labor and material modeling expertise. Instead, we made an algorithm to learn our preferences and recommend high-quality materials. That's right. All these materials were synthesized by a learning algorithm. So if you like computer graphics, machine learning, and beautiful images, come see our talk on Tuesday.
Modeling 3D objects with realistic surface appearance is challenging and time-consuming, even for experienced modeler. We present a method to extract a rich, non-parametric appearance model from a single image. The extracted model may be used to assist in modeling detailed and realistic 3D models. Want to know more? Come Tuesday.
Developable surfaces desirable for manufacturing are often thought of as flattenable surfaces, but this includes ugly, non-smooth surfaces like crumpling a sheet of paper. Instead of the classic angle defect, which gives flattenable surfaces, we introduce a novel definition. The normals around every vertex should be contained in a common plane. This condition can be used to push surfaces towards beautiful piecewise developables. We use it to design and fabricate developables in many domains. Come to our talk to find out more. So we have noisy data on a surface, and we want to smooth it to get rid of the noise. But if our surface has a boundary, this will bias the result. We use the Hessian energy to mitigate the influence of the boundary. This also enables us to interpolate data while ignoring holes in the domain, or use L1 optimization for piecewise smooth data. While the Laplacian gives ugly, spiky results, the Hessian gives pleasant, piecewise planar results. Come see how.
We present a computational approach for designing and fabricating zippables. Zippables are objects which are made from a flat piece of fabric with a single zipper band attached around its boundary. Zipping them up creates surprising 3D shapes, like this star shape. In our talk, we will present a parameterization-based method to design zippables for a wide range of target shapes, and show you how they can be easily fabricated without much expertise.
In real-time physics-based animation, we currently have to choose between artificial numerical damping and unstable behavior. The idea of our method is to blend together different integration schemes. This allows us to produce vivid animations and guarantee that explosions won't happen. We will also discuss the stability of backward Euler in the nonlinear case. Later, we generalize this approach. Explosions and artificial damping are caused by numerically violating Noether's theorem. One way to encourage correct behavior is to project the results of an arbitrary integrator to the constant energy manifold. Our new fast energy projection enables us to produce vivid yet stable animations, such as this funny-looking rabbit, or this delicious plate of Jell-O.
Consider the elephant. For decades, researchers have been trying to simulate it as a lifeless skin to then pump it up with air and let it rise into the sky like a balloon, to whirl it around or use it like a basketball. We finally make this possible, and as a byproduct, create a framework for the real-time simulation of meshes of arbitrary resolution. Thank you.
Light transport is hard. You can solve it in multiple spaces, and with many different strategies. Sadly, they all fail in different ways, and so it's bad if your renderer gets stuck using just one of these. We show how to use some cool math to teach Metropolis light transport to jump between different spaces and between different strategies. If you want to learn how to get your renderer unstuck, come see our talk on reversible jumps on Tuesday at 2 p.m.
Participating media generate complex lighting effects when interacting with geometry. Path tracing methods robustly compute these effects, but usually ignore the redundant information from nearby points. We present a new method for efficient rendering of participating media. We estimate media radiance derivatives and use them for adaptive sampling and extrapolation. Our method is rebounded and accounts for occlusion changes in single and multiple scattering. If you want to know more, please come to see us on Tuesday.
Rendering participating media is challenging, and many specialized techniques have been proposed to reduce noise and improve efficiency, including volume photon mapping, beam radiance estimate, and photon beam. In this work, we introduced the first gradient domain light transport formulation for participating media, resulting in efficient volumetric density estimation algorithms that works for photon points, beams, and planes. See you at our talk on Tuesday.
This is a photon, and this is a medium consisting of many uncorrelated particles. As predicted by the RT, when a photon collides through the medium, it will collide with exponential probability. But what happens if the particles are correlated? In our work, we present a radiative framework for spatially correlated media. Come to see our talk to check out how our photon finds its path in a correlated world.
We propose turbine style transfer. So two flows with the desired global and detailed motions are input to our system, and then the detailed motion is transferred to the global motion. So each motion can be designed separately. And detailed motion can be reused and repeatedly transferred to various global motions. So please come to our talk. Thank you.
Implicit incompressible SPH solves the pressure-Poisson equation. While the solution of the PPE provides pressure at fluid particles, the embedded boundary handling does not compute pressure at the boundary. We propose a novel method that overcomes previous IISPH issues by globally solving for pressure values at the boundary. We show benefits such as improved solver convergence, larger time steps, and reduced oscillations. Thank you.
For coupling solids and fluids, the partitioned approaches provide one convenient way without knowing the interiors of the system. However, they might take too long to converge, might be unstable, and fail to handle closed regions. We propose an extended partitioning method with multiple components that is faster, more stable, and that can handle closed regions. We demonstrated that our method can work in stiff and complex scenarios with small overhead. Please come to our talk for details.
So a few years ago at SIGGRAPH, there was this great new eigenfluid-based method for simulating fluids. You can get all these interesting new flows. The problem is this method's a big memory hog. So at 27 gigabytes, we ran out of memory. So we show how to pump up the scalability by a factor of 1,000. So this would have taken 6.1 terabytes of memory using the old way, and we can do it in the same amount of memory using the new way. So we're also 100 times faster. So we're 1,000 times smaller, and we're 100 times faster, and we actually support more types of boundary conditions. So come see how on Tuesday.
Enjoy the flight.
Touch the sky. We worked on it every night and day.
See you Tuesday.
We present a new aerodynamic simulation algorithm, also a user interface for glider design based on the assembly parts. We accelerate the previous method in real time very fast. We also that the user can edit the glider by assembling each part. The system continues to present the flight simulation results. Using our approach, the glider can fly very well. Welcome to our talk.
Generating a long, uncut, high-quality aerial video footage with drones is highly challenging. One has to both pilot the drone and simultaneously control its camera, a very skill-demanding and exhausting process. We introduce a novel trajectory design tool, which enables even novice users to automatically plan a complete and smooth camera flyby for a large-scale outdoor scene. Want to know more? Come Tuesday. Thank you.
Engineers use fluid simulation to design aerodynamic objects, but it is very time-consuming and expensive. So our goal is to machine learning fluid simulation for 3D objects. Our contribution is to use a polycube mapping for the shape parameterization. We achieved real-time fluid prediction during the interactive shape editing. And we can handle arbitrary topologies. Come to our talk in Tuesday evening.
Drones with gimbal-mounted cameras open the door for everybody to create spectacular aerial videos. However, a lot of users struggle with controlling the drone and the camera at the same time, resulting in non-smooth, unpleasant footage. In our talk, you will learn about our method that takes novice-designed flight paths and generates expert-like drone camera trajectories.
This contribution is based on a series of works of mine that I did during my artist in residency at the Pilchuck School of Glass in 2017. Together they form the argument of a digital craftsmanship that is based on the integration of 3D scanning and 3D printing into traditional glass blowing and glass casting workflows. Please enjoy the talk on Tuesday.
Hologem in Wonderland is the world's first multi-person co-located live theater piece performed entirely in untethered room-scale virtual reality. Using sensor fusion of Gear VRs and Vive trackers, audience and actors share a magical world based on the work of Lewis Carroll, where people turn into butterflies and mushrooms grow as tall as trees. In the immortal words of Lance Williams, the possibilities are limited only by your imagination. Thank you.
Inhabita is a mixed reality artwork of creative exploration within an alternate ecosystem. We invite participants to become part of this world through three perspectives of scale and agency. Just as biology continually rears itself, we use runtime code generation for open-endedness. Anticipating futures saturated in interconnected computation, we must also plunge deeply into what nature is to find our place within it. Thank you.
Enjoy the video. Welcome our talk on Wednesday.
We present a modeling tool that allows users to create and edit N fields in real time using hard constraints on directions or singularities. Higher order energies allow for consistent solutions, and we demonstrate the power of our tool onto novel interactive applications.
Octahedral fields have been used to produce high-quality hexahedral meshes. However, little attention has been given to the structure of their singular graphs. We enumerate all practically relevant singular edges and vertex types and prove a global index theorem. We also develop an algorithm that takes a user-specified singular graph and generates a corresponding octahedral field. Using our method, the user can control the singularities of the resulting hexahedral mesh.
We present a real-time simulation for detailed water waves, where objects float and emit waves with simple coupling method, which scales well to large scenes like these 1,000 barrels. Waves also nicely reflect of solid boundaries, and we still get a real-time performance for huge scenes like this one. To find out more about the beautiful math which made this possible, come to our Wednesday talk.
We present a deep learning-based method to upsample smoke simulations from data. Here you can see a generated example. We actually train 3 networks: a generator, a regular discriminator for detail, and a novel one for temporal coherence. The network also profits from an inductive bias for transport, which improves convergence. So we hope that with our results, some of you will actually join us on the the deep side of learning for physics. See you.
Imagine 2 players are playing a volleyball game, but they have to control the ball indirectly by shooting water at it. How can we control this coupled fluid rigid body system? We design a deep neural net controller trained using reinforcement learning. After training, our fluid AI can accomplish challenging tasks such as volleyball playing, or moving a floating ball on the water surface, or pushing the ball to multiple target positions on the ceiling. Come to our talk to learn more about this fluid AI.
See you on Wednesday.
Thank you.
The computational cloud provides huge, low-cost computational resources at a per-hour basis. Nimbus is a software system for automatically distributing Eulerian and hybrid simulations in the cloud. Nimbus uses a novel 4-layer data model to automatically stitch together many sub-simulations. Experimental results show that Nimbus can run bigger phys-band water and smoke simulations faster. Nimbus is open source, and we encourage you to use it and try it.
Sketches are used in various modeling and image manipulation settings. Sketch processing algorithms expect clean line drawings like these ones, but in reality, artists routinely use multiple inexact raw strokes to depict intended curves. We introduced Stroke Aggregator, a robust algorithm for consolidating raw artist drawings into clean sketches suitable for subsequent processing. Our method clusters input strokes to produce clean line drawings that are consistent with viewer expectations.
To learn more, come to our talk on Wednesday. Thank you.
Sketch simplification is the process of converting rough sketches into clean line drawings. While data-driven approaches show great promise, their applicability is limited by data bias. In this work, we propose a semi-supervised framework that outperforms existing approaches on challenging rough sketches. Furthermore, our framework can be used to perform the inverse problem of pencil drawing generation from line drawings, simulating different artists. We present a data-driven framework for the semi-interactive inking of rough sketches. Our approach automatically inks a rough sketch while allowing the user to intuitively correct and edit the results. We present 3 tools for effective inking. The inker pen allows to find grain control. The inker brush is for quickly fixing missing strokes. And the Smart Eraser can easily erase unnecessary strokes. If you're interested in sketching, please come see our talks.
Realistic image editing is a challenging task. Experts spend considerable amount of time on photoshopping images to produce plausible results. We introduced FaceShop, an interactive framework that enables the synthesis of high-quality edits with just a few user-provided strokes. Within minutes, our framework can produce realistic results of complicated edits that would be challenging and time-consuming using Photoshop even for skilled users. Want to know how it works? Come to our talk. Thank you.
X-ray computed tomography is an extremely valuable tool for revealing the internal structure of objects. However, traditional X-ray tomography fails in reconstructing dynamic objects, and in this paper we present a joint space and time reconstruction that actually fixes this problem and really provides highly detailed videos of deforming objects. So if you want to see roses wilt or dough rise, then come to our talk on Wednesday. Thank you.
What if you could revisit your favorite vacation spot in VR? We present an algorithm that aligns color and depth images from a standard dual-camera phone in 3D. Our app captures bursts at about 1 image per second. We align these bursts, making the depth consistent and seamless. This is fast and takes about the same time as the capture. The result is a highly detailed 3D panorama that looks fantastic in VR. Please come to our talk on Wednesday for the details.
Reconstructing 3D scenes with mirror and glass surfaces is a hard problem. Inspired by the long-standing challenge of people taking snapshots of their own mirrors, the key problem is how to take a photo of your mirror and not photograph yourself.
Especially in the bathroom. By enabling reconstruction of these scenes, we can re-render the scenes perfectly with the people removed, both into video and photographs. To find out more about our new 3D reconstruction system, come to our talk on Wednesday.
So we propose an algorithm to reconstruct a transparent object. Apparently, optical scanner or multi-view stereo are not suitable for this task. We built a special automatic system to capture how the background patterns reflected by the object, which could be used for inferring the detailed surface geometry. Combined with novel point consolidation methods, our algorithm can nicely recover the surface geometry and reproduce their light refraction properties. Come to our talk on Wednesday morning. Thank you.
When a robot enters an unknown room, how can it explore and understand the scene? We observe that a human prefers to visit exhibit by exhibit when she looks around a museum. Inspired by this, we present an object-aware auto-scanning system to let robots scan an unknown scene object by object. With the guidance of objects, our method can automatically obtain exploration, reconstruction, and understanding of the scene in one navigation pass.
Please come to our talk on Wednesday. Thank you.
We revisit the classic problem of conformal flattening, showing how a deeper understanding of boundary conditions turns it into a powerful and modern tool for surface parametrization. The key insight is to use a pair of Poincare-Steklov operators to compute boundary data, then to extend to the interior. This enables real-time and robust editing of high-resolution maps with minimal area distortion, direct editing of boundary lengths or angles, sharp corners, cone singularities, and arbitrary target shapes.
A holy grail of geometry processing is finding surface flattenings with minimal distortion. And for interesting surfaces, you really need to do some kind of cutting. All existing methods are based on greedy local heuristics and non-convex optimization. We present the first method that provides globally optimal solutions. More precisely, we find the best cones that result in conformal flattenings with minimal distortion. The algorithm is extremely easy to implement and requires nothing more than some sparse linear algebra.
Given a three-dimensional target shape, our method designs a flat material that has a 3D shape encoded in it. The encoded shape can be rapidly deployed by either inflation or simply letting it hang under gravity. We explicitly characterize the shapes that can be made in terms of conditions of scaling and mean curvature, and our method is applicable on any scale, from tiny hard stands to architectural scale domes. Hope to see you there.
We'd like to fill space with blue noise, but without large gaps. In high dimensions, one of the few scalable methods uses point sampling in a local neighborhood, but it can still leave big gaps. Spoke darts replaces point sampling with line samples and comes with a guarantee that any gaps are probably small. Applications include motion planning, rendering, geometry, and optimization.
Thanks for watching.
We present a fast technique for directional wave acoustics. Thanks.
Analogous to general framework for visual rendering, we propose an integrated approach to synthesize high-quality animation sounds. Our system uses an accurate finite difference time domain method with a novel parallel in time technique. It can render general animation content, such as this bowling ball, or this realistic water sounds. Thank you.
We simulate the sound of thin shells. We capture the linear, the nonlinear, and the turbulent components of sound. We even compare results to real experiments.
In 360-degree videos, spatial audio is crucial for immersive audio-visual experience. Traditional mono-channel audio cannot convey the spatial context, as shown in this example.
The quick brown fox jumps over the lazy duck. The quick brown fox jumps over the lazy duck.
Our method can synthesize immersive ambisonic audio.
The quick brown fox jumps over the lazy duck. The quick brown fox jumps over the lazy duck. The quick brown fox jumps over the lazy duck. The quick brown fox jumps over the...
Please come to my talk to learn more.
We use both vision and audio to separate speech. You can take a video, select a person, and then hear only that person while everything else is muted.
Here's said it's all right to lose on purpose
of course
and advertise that to the fence.
Who doesn't
it's
know
perfectly
that?
okay.
Now let's see our results with only the speaker on the left.
You said it's all right to lose on purpose and advertise that to the fence. It's perfectly okay. You said it's okay. We have nothing else to talk about.
We have a lot to talk about. Come to our talk.
Hi. Humans use letters, which are two-dimensional static symbols. To write letters, we have to move our body and spend some time. So it can be said a letter is a trajectory of movement and time. Based on this notion, we studied 3 types of kinetic typography, mainly using robots. Please come to our presentation on Wednesday.
We are a design research lab working
How
on
can we bring
sustainable
digital
innovation.
heritage back to life?
So we combine new
How can we
technologies to
revive
create
an event
meaningful user
charged with the
experiences.
intensity of a live performance?
To revive audiovisual heritage, we can
5,000
provide
hours of
principles
concerts
of
to
interaction,
pass on to future
physicality,
generations.
and augmentation.
6
So
years
for
of research.
augmentation, we use real-time
Welcome to the
up-mix
Montreux
audio
Jazz
techniques
Heritage
by
Lab.
Illusomic. For physicality, we play with architectural screens involving aluminum 3D printing and evaluate user perception, emotion, and cognition.
Have you ever 3D scanned a castle and then be disappointed to get results like this? You can maybe tell that it's a castle, but not much more. Won't it be nice to be able to make out individual bricks in the 3D scan, something like this here? We propose new time-of-flight camera designs that can potentially achieve laser scanning resolution at long ranges. Our cameras currently look like this, but hopefully we'll be able to fit them in a pocket in the future. Thank you.
LiDAR calculates distance by measuring the time it takes for light from a laser to travel to an object and back. If the sun comes out and our pirate moves far away, we need to increase the laser power to see the return pulse in the measurements. Too much laser power might not be safe, though. At long range, under strong ambient light and low power, the return pulse is difficult to make out. But with our approach, we can robustly recover 3D geometry using an intensity image in less than a single detected laser photon on average. Come to our talk to find out more. Thanks.
In the animal kingdom, brains and eyes have co-evolved to form a dazzling variety of domain-specific visual systems.
While our computer vision pilots solve widely different problems, their optics all follow the same principle of creating a sharp image before processing it. Instead, we propose to optimize the optics end-to-end with high-level processing to form true domain-specific cameras.
We optimize and fabricate custom optics to tackle real-world challenges such as extended depth of field. Come to our talk on Wednesday to learn more about end-to-end optimization of cameras. Thanks.
Thank you.
Adaptive optics has been developed in applications for like astronomy for removing small wavefront distortions from image formation process. However, if we're talking about normal cameras, we have to expect much, much larger distortions, for example, water drops on your lens. And in this paper, we actually present the first megapixel adaptive optics system that's specifically designed for these kinds of applications, where we have major distortions and can remove them in hardware rather than in software. If you're more interested, no, sorry.
Please come and see what just happened. Thank you.
We present a normal framework to render scale-aware black and white abstraction from 3D shapes. We model a problem as a graph labeling optimization guided by identified design principles. Our framework runs at interactive rate and is fully automatic. Potential applications include flat design and thumbnail generation. Come to our talk to learn more.
Semi-structured images with perceptually distinct regions and clear boundaries are natural candidates for vectorization. Large numbers of such images are saved in raster form, but existing state-of-the-art vectorization methods fail with multiple visual artifacts. We present a perception-driven algorithm designed for semi-structured images that produces vectorized outputs well aligned with viewer perception, enabling applications such as artifact-free resizing.
Come to our talk to learn more.
Detailed nonlinear elastic deformation requires high resolution input, so the time cost is very expensive. By optimizing bases, we can get a similar behavior on cross mesh with faster performance. Our method can apply to any homogeneous, nonlinear, anisotropic elastic model. For more details, come to our talk on Wednesday. Thank you.
I'm going to present a work for magnetic simulation. First of all, it's stable. Secondly, mutual induction. The ion balls induce each other, so we can see a chain of the ion balls. Finally, resonance. The nail is not a magnet, but it's rubbed against a bar magnet. Then the nail acts as if it is a magnet. And we can see the ion balls being lifted. How nice! I will show you on Wednesday more.
Volume simulations are a great tool for generating animations like these, as they can naturally generate flesh-like features and details. These types of sims can be difficult to run with existing models, however, which motivated our development of a new model for volumetric flesh sim. Our new model is robust under inversions, is stable under large deformations, and conserves volume well. To learn how we generated all these animations with our new model, please come see our talk on Wednesday afternoon. Thank you very much, Vancouver.
This work is about manipulating the appearance of dance in video. What auto-tune does for those who can't sing, this work does for people who are bad at dancing. I can take a kitty cat and I can make it dance. Take a politician, what's he missing? Obviously jams. Take anything you see and rip right off the screen. Turn it around and align with the sound of music of your choosing. So get to the session early and grab a good seat, because at 3:45 on Wednesday, I'm gonna drop the visual rhythm and beat.
Writing and drawing has evolved from traditional tools to modern digital devices. However, the digital convenience comes at a cost of lost haptic feedback, something artists try to regain even if they have to return back to the paper. In our work, we combine insights from haptic perception experiments with custom numerical simulation and multi-material 3D printing to design novel stylight that better mimic traditional drawing tools. If you want to know how to combine all of these ingredients, please come to our talk.
Everyone uses the sense of touch to explore the world, but quantifying tactile feeling is difficult. Our model for tactile roughness can help. It closely matches human perception and can be used to control tactile feel in 3D printing applications. Consider this little gecko. Using our model, we can alter this lizard scale height map to fabricate 3 scaly geckos that feel distinct. We can do the same with this burlap texture height map to fabricate 3 geckos that match the first 3. Come to our talk Wednesday to find out how we do it.
Hello, everyone.
Image quality metrics are computational judges who say whether an image has good or bad quality by assigning a score. But they can be easily deceived when the distortion is localized. To address this problem, we propose a new localized visibility metric based on a convolutional neural network. The proposed metric can tell us whether and where the distortion is visible. For more details, please come to our talk on Wednesday afternoon.
Thank you very much.
Hello, would you like to render images like this, but your path tracer is too slow? Maybe your direct illumination sampling ignores visibility of lights and wastes samples on the invisible sun. But with a little help from Mr. Bias, we are able to learn the visibility of lights and thus improve the direct illumination sampling, and consequently speed up the entire rendering. Please come to our presentation to see more. Thank you.
We achieve high-quality image-based relighting results from only 5 captured images by using a deep convolutional neural network. We train our network on procedurally generated synthetic scenes. Our network learns the optimal light directions and a function to relight the scene and the frontal directional light simultaneously. Then we can capture a real scene under the 5 optimal lights and relight it under directional lights, which allows us to do environment map rendering. For more details, please come to our talk on Wednesday. Thank you.
High-quality reflectance can be captured by imaging under different lighting, followed by a reconstruction from photos. Here, the lighting patterns and the reconstruction scheme are manually derived by researchers in all existing work. To save some time for these guys, we use deep learning to do the job automatically, resulting in as few as 16 patterns corresponding to a capture time of 12 seconds. Want to know more? Come to our session on Wednesday afternoon.
Thank you.
A single picture is typically not enough to capture the appearance of a material. If used as a texture, it simply fails to reproduce smooth shading effects. Our rendering-aware deep network retrieves a physically based material model, producing a realistic appearance. Using our method, it is now easy to capture materials in your surroundings, like these few hundred results we captured just a couple days before the deadline. See you on Wednesday.
We introduce a novel metamaterial that strictly enforces all the geometric constraints of fused filament fabrication, such as continuity of deposition, self-supporting geometry, and maximum overhang angles. Our microstructures span a range of elastic behaviors that can be precisely controlled by the user. Join us on Wednesday.
Modern industrial knitting machines can make three-dimensional surfaces, like these, seamlessly without the need to cut, sew, or glue. We present a method that takes a 3D model and a time function as input and generates knitting instructions to fabricate these models on an industrial knitting machine. We've tried our method on a number of models, including these silly hats. Come attend our talk on Wednesday afternoon to learn more. Thank you.
Hey, Queen. How you doing?
Hi, Jim. Could you knit a sweater for me?
Sure.
Oh, a bunny.
I wouldn't know how to knit that.
Oh, a dragon.
Well, that seems even more complicated.
Or elephant, or cat, or lion, or horse, or armadillo.
Wait, I don't think you understand how difficult it is to figure out how to knit something.
Oh, come to the talk, and I will show you the method that can automatically convert any shape to a stitch mesh.
Any shape I want?
And fully automatically.
Whoa.
We can even print them.
So you want the sweater or not?
No, I want the bunny.
Hi everyone. I believe many of us have the experience that the jeans, pants we bought online or even in store are too tight or too short for us. And for girls, we usually wonder how do we look like in that when we dress in that beautiful dress in one image. So in this paper, we present a method to reconstruct 3D garment together with the material properties from a single view image. Come to our talk on Wednesday afternoon to learn more. Thank you.
Fourier, can we reverse engineer the woven cloth model from a photo?
Oh, that's actually quite a challenge, but I might have some trick in my space.
Boom, boom.
Come join us to get upholstered, 3:45 Wednesday.
And Lego on us says, be there.
Creating a transforming pop-up is a big challenge even for experienced paper artist engineers. We provide a fully automatic algorithm for creating a transforming pop-up. All you need to do is input 2 patterns. And we demonstrate our method on a variety of real-world examples. For more details, welcome to our talk to learn how to automatically generate a structure of transforming pop-up.
Thank you.
Design objectives are often conflicting. A wrench should be light and strong, but improving the design on one axis will decrease its quality in another. We present a new approach to navigate the landscape of compromises effectively, to discover solutions that are optimal under different design trade-offs. So come to our talk on Thursday and learn how to make optimal compromises.
Do you like digital sculpting but find it difficult? Our autocomplete 3D sculpting system can help you. When you sculpt, our system produces the next steps and visualizes them in yellow colors, including large deformations and small details. You can accept or ignore the suggestions to maintain full control. Welcome to our talk on Thursday. Thank you.
We introduced Fold Sketch, a new system for adding folds and pleats to clothing and other cloth objects. Real-life garment folds have complex profiles, and creating them using purely geometric means is an impossible task. Unlike traditional designer workflows, which depend on trial and error, Fold Sketch lets users specify their desired folds and pleats using a simple schematic sketch-based interface. Fold Sketch then generates both a new 3D cloth object that matches the designer's specifications and a new set of 2D patterns that reproduces these folds under physical simulation and in real life. For more information, come to our talk.
Thank you.
We present a new method to fabricate 3D models on a robotic printing system. The materials are accumulated inside a volume along curved passes. Compared to traditional 3D printing, we can reduce the support structures tremendously. Our major contribution is how to generate curved layers at the same time considered hardware constraints. If you want to know more, come to our talk.
Stanford bunny. Of course we love bunny. Then why don't we need many bunnies? Our method generates molds for fabrication, for replication. Then we can make many bunnies with this mold. 3, 2, 1. Thank you. Come to our talk.
See you on Thursday to learn about metamolds.
Despite the popularity of 3D printing, subtractive manufacturing remains the dominant technology today. We extend connected ferment spirals, which we introduced at SIGGRAPH 2016 for 3D printing, to CNC machining. The ferment spirals now represent carving paths over curved surfaces that are designed for uniform spacing and improved surface finishing. But before carving, we have to decompose the object surface based on accessibility by the cutter. To learn more details, please come to our talk.
Thank you.
Alex, I'm trying to find the craziest videos from last year's Fast Forward, but my Python script is just too slow.
I can help you with that, Will.
Wow, that's awesome. How did you do that?
Well, I use Scanner, our open source system for efficient video analysis at scale. We've also used Scanner to accelerate VR video synthesis, markerless motion capture, and the analysis of a huge TV news data set, all using hundreds of machines in the cloud. To find out more, check out our website or come to our talk on Thursday.
Gradient-based optimization is becoming central to modern image processing and deep learning. But writing fast gradient code for new operators is tedious. Deep learning frameworks are limited due to their use of coarse-grained operators. We propose an automatic solution that is both more flexible and faster. We can preserve parallelism and allow exploring different trade-offs. We'll also show you a new way to think about differentiable image processing. Thank you. Come to our talk on Thursday morning, maybe.
Over the years, we have seen more and more programmable stages added to the graphics pipeline. The pipeline structure itself, however, remains fixed. State-of-the-art rendering increasingly relies on compute mode and complicated multipass approaches. But what if we could simply make the pipeline fit our application rather than make our applications fit the pipeline? How fast could we make a software graphics pipeline run on a GPU? Come to our talk if you want to find out.
Real-time renderers must be modular and extensible while achieving high performance on heterogeneous platforms. To support shader specialization and efficient parameter communication, developers use preprocessor hacks and ad hoc code generators that are hard to maintain and adopt. We propose SLAN as an extension to HLSL with a set of general language mechanisms to replace ad hoc tools, and it is now the shading language for NVIDIA's Falcor rendering framework.
Deep reinforcement learning can produce unnatural behaviors. Motion quality can be drastically improved by imitating human demonstrations. We present a deep reinforcement learning framework that can learn a huge variety of skills from motion capture clips. Motions can also be retargeted to characters with drastically different morphologies. If you want to train a lion, well, we can do that too. So come to our talk to check out all the skills that our characters can learn.
Hey, robot. I'm going to teach you how to walk like I do. No motion data for you, no finite state machines. Okay, first try walking forward without falling. Now try using less energy. You know that's not what I meant. That's better, but something's still missing. Be more symmetric. There you go. Now you know how to learn walking from scratch. Go teach your friends how to do it. Thank you.
We present the first purely data-driven method for real-time quadruped motion synthesis called mode adaptive neural networks. Our system can create production quality animations from unstructured motion capture data and does not require any labels for the phase or the locomotion modes. All motion is directly generated and controlled in runtime and does not consist of any keyframed animations. And if you want to integrate the next generation for character animation in your future projects, get in touch or come to our presentation Thursday morning. Thank you.
If you work with polyhedral models, you may use T-junctions to either start or end features. And you may want to use those models as control structures to associate smooth surfaces with it. So here's an example that has a T-junction there in the back and the usual multi-sided things that we can already work with and make them disappear. The goal on Thursday is to make those T-junctions disappear, so come for some tea on Thursday.
Oh no, this plastic armadillo has been hit with a heat ray. Luckily, we can simulate the effects of heat and moisture on thin shells using ideas from differential geometry. Our method matches experiments where water diffuses through a slip of paper. We can also extend this method to incorporate features like anisotropic growth, which drastically changes how these paper rings curl up. For more details, come to our talk Thursday morning.
Thank you.
We present a new NPM scheme for simulating fluid sediment mixture. Our method captures the two-way coupled sand dune migration and turbulent sediment transport, where the sediments are carried over an obstacle by the fluid. And also sedimentation, where the sediments interact with the fluid, generating intricate vortices before settling down. Welcome to our talk on Thursday. Thank you.
Question: do you like the material point method? NPM is my favorite, but it's a bit hard to implement.
It would be great if NPM runs faster, so that I will suffer less.
Our novel moving least squares material point method runs fast and can be implemented in 88 lines of code. We further introduced the compatible particle cell method to enhance NPM with cutting and two-way rigid body coupling. Our high-performance implementation is open source with the TaiChi computer graphics library. Thank you.
We present a machine learning method for analyzing styles of 3D shapes. The key features of our method include the use of projected feature lines for style presentation, semi-supervised learning via PSLF, the ability to spatially localize stylistic elements. Huh? What is PSLF? Public Service Loan Forgiveness? No, it is partially shared latent factor learning. To learn more, please come to our talk.
See you on Thursday morning.
Thank you.
Humans can predict the functionality of a 3D object by hallucinating a usage scenario involving the object. In this work, we introduce a sequence of predictive and generative deep convolutional neural networks to replicate this human capability. Given different objects in isolation, we are able to predict the corresponding functionality of each object by inferring their functionality revealing interaction contexts and even explore multiple functionalities. Want to know more? Come to our talk on Thursday.
Thank you.
We propose a new method for encoding the shape context of a given point. We simulate a discrete time evolution process on surfaces. Our method performs well on shape matching with strong deformations and partiality. Please come to our talk.
We introduce P2P-Net, a bidirectional deep neural network for point displacements which transforms shapes between two domains. For example, mesoskeletons and surface samples. With the same network, we can convert cross-sectional profiles to surface samples and back. And as another example, from partial point scans to complete services and back. P2P-Net is designed as a general-purpose point displacement network. To learn more details, please come to our talk.
Thank you.
Predictable models are very popular and nice for many different things, but when used in simulation results are very sensitive towards the quality of contact points. This work presents a methodology for assessing quality of contact points, and we also present two new methods for generating contact points. If you're interested to hear more and learn more about how to compute contact point, then please come to this talk. Thank you.
The packing efficiency of texture atlases of a 3D model has a strong impact on the quality of the rendered result. We present Box Cutter, a method for optimizing packing with just a few shortcuts. Compared to the state-of-the-art, the resulting texture maps exploit their pixel budget more efficiently, leading to improved visual quality. And if you like, you can also use our method to craft polycube bunnies with less paper. Come see our talk on Thursday.
We process signals directly in a texture atlas, exploiting grid regularity while handling chart boundary and parametric distortions. Applications include stitching, smoothing, sharpening, line integral convolution, and geodesic computation. Using a multigrid solver, we obtain these results interactively. Thank you.
Do you remember the last time you tried to UV map an imperfect mesh? Existing automatic methods produce irregular patch boundaries and a lot of wasted space in the texture. Generalized motorcycle graphs can help. Our methods partitions all your quad-dominant meshes into quadrilateral patches, and those are easy to parameterize and pack in a texture.
Most surfaces cannot be flattened without a lot of stretching. Luckily, we can make cuts. But which cut should we make? For the first time, we formulate the low distortion surface cutting problem in the smooth rather than discrete setting. We show that combining conformal geometry with shape derivatives yields a remarkably simple flow for low distortion cuts. Our method generates smooth solutions with arbitrarily low distortion, making it well suited for fabrication. Come to our talk and learn more.
We present a simple and practical method for joint color and translucency fabrication. And it just uses RGBA textures and the geometry. And it reproduces not the physical quantities like light transport, but just perceptual cues. So if you are interested in the talk, then go on Thursday to the session on fabrication for color and motion. Thank you.
We propose a method for fabricating VRDF reflector. So the reflector shows different images depending on different viewing direction. So the mirror shows different images. Also, depending on lighting direction, the reflector shows different image. So please come to our talk.
Imagine 3D printing small objects like this, but smaller. No, much smaller. Yeah, better, but still smaller. This is what we did. And from these transparent nanostructures, we obtained color without using any pigmentation. So come to our talk to hear about structural coloration, electromagnetic simulation, and nanoscale 3D printing. Thank you.
Having troubles coordinating your legs and wheels? Try out our new design system. It lets you create your personalized legged wheeled robot and generate agile and physically valid motions. 3D print your creations and let your robots do the skating. Thank you.
We present VismNet, a novel deep learning-based approach that is able to produce animator-centric speech-motion cues and automatically derive modern production phase rigs directly from input audio alone.
我们提出一种基于深度学习的方法 VismNet， 该方法能够生成面向动画师的语音运动曲线。
Laurel.
Yanni.
Come see our talk Thursday afternoon. Ladies and gentlemen, hey, come on! Hey, come on, bro! Nice to meet you! どうぞおかけください。今日は嬉しい。今日はね、歓迎の意味を込めて日本語のダンスを用意してきましたので、ジャパニーズダンス。はい、いきます。はい、トトンがトン、トトンがトン、はい、トトンがトン、トトンがトン、トトンがトン、トトンがトン、トトンがトン。トトンがトン、ボブボブボブボブ、よう来たな、ボブ。
Thank you.
Deep video portrait transfer the face pose, head pose, facial expression, and eye gaze from source to target video. Our approach also enables interactive face editing in video. So here in this example, we first transfer, we edit facial expression by pulling the corner of the mouth. For more fun with the faces, please join us on Thursday. Thank you.
We will also present our recent work called Head-On. Head-On is able to reenact the upper body of a person. It includes the transfer of facial expressions, head movements, gaze, and torso motions, all without deep learning. At the core of the method, we reconstruct a 3D avatar of the target person that can be controlled by any other person in real time. See you on Thursday.
Breaking things is easy. Fixing them, on the other hand, is often very hard. This is particularly true for motion capture data, where occluded and swapped markers often require tedious manual cleaning to fix. Yet by breaking motion capture data in millions of different ways, we found it's possible to actually learn to automatically fix it. Come to our talk to see how we build an optical motion capture solution which is robust to errors in the input and removes any need for manual cleaning of data.
We present MonoPerfCap, the first human performance capture method for monocular video. Our method not only tracks the articulate motion of the human body, but also capture the non-rigid deformation of the skin and clothes. Our result can be used in many applications, such as computer animation, field viewpoint video, and telepresence. To learn more, please come to our talk on Thursday afternoon. Thank you.
Hands. Hands. Hands.
Nice to meet you.
Deep labels. Hands.
Come see our talk.
On hand tracking.
Thank you.
Hi, I know how you feel. It's really demanding. You actually realize this SIGGRAPH is about sitting and sitting and sitting and sitting. But no worries. Actually, if you come to our session, we'll be doing real exercising. So you can enjoy some slow motions, some real fast motions. It can be also jumping, and of course, dancing. So see you then.
All right. What about a last round of applause for all the speakers because they did a fantastic work. Thank you also to Munu and Adobe for sponsoring the program. That was fantastic. Thank you so much. And I'm going to leave you with 3 action items. The first one is tomorrow morning there will be the awesome and epic opening of SIGGRAPH, the real opening. So Roy is going to welcome all of you. So please make sure to wake up early for this. Second thing, you have to recycle your wristbands. There will be a box right next to the door when you leave the room. So please recycle them. And the third thing is enjoy SIGGRAPH. It's going to be a crazy week, but you're going to love it. So enjoy. Thanks.